We're going to do a review of where we have been the last several weeks, and for the midterm on Friday. As I told you before, the midterm will cover chapters 4, 5, 12, and 13. 4, 5, 12, 13. Like the first midterm, there's going to be 4 problems, 25% each, equally weighted. Made a guessing game. Let's see, 4 chapters, 4 problems. Okay, I think you know what's going to happen. Let's go through quickly chapters 4 and 5, and then we're going to spend most of our time on chapter 13. Since I passed back that homework today, and there's homework due on Friday in chapter 13. Okay, 2D conduction. Been a while. Number 1 is you want to be able to write out the differential equation, so write out the differential equation for the particular problem with boundary conditions. We did that for one on the board, a rectangular plate with different temperatures and the boundary conditions specified for certain x values and certain y values. So review that in your class notes. Number 2, we then said we're going to do a graphical approach called a flux plot. So a flux plot, heat flux plot. On the flux plot, we're going to show adiabats and isotherms. And on that plot, you have to follow a set of rules in making these plots. They must cross at right angles, interior. When they come to a boundary, is the boundary adiabatic or a constant temperature, and they do certain things on the boundary. If they come to a corner, which is isothermal, they bisect the corner, things like that. So you have the rules written down. So that's called flux plots. And then we had the conduction shape factor. That was capital S, and the Q then, heat transfer between 2 surfaces in 2D heat transfer was SK T1 minus T2. If you want to express that in the form of a resistance, this is T1, this is T2, this is Q, this is 1 over SK. Those values were in chapter 4, and we worked several problems in class, and you had several for homework involving that, the S value. And let's see, there it is, table 4.1. And we had a problem, I think we worked in class and for homework, where you had to combine these resistances with convection. So you can also have convection resistances from surfaces, so you could construct an equivalent thermal circuit, including conduction, the S is the conduction part, with convection on the inside surface or the outside surface, whatever it might be. Okay, so that's chapter 4. It is somewhat brief, and there's not a lot in it as far as compared to other chapters, but anyway, those are the main high points of that chapter. Anything on that before we go into 5 then? Yeah.
So we won't be given like the sort of mesh of something like
Nothing with numerical methods, no.
Okay.
That was a special problem. Yeah, so nothing on numerical methods, good point. Chapter 5. Transient heat conduction. Okay, first step we know in chapter 5 is find the BO number. All right, find BO. If BO is less than 1/10, use lump heat capacity. If BO is greater than 1/10, use approximate solutions. That particular BO is HL over K, or HR naught over 2K, or HR naught over 3K. If it's a plain wall, it's the first one. The wall thickness is 2L. L is called the half wall thickness. If it's a long cylinder, the characteristic length is R naught over 2. If it's a sphere, the characteristic length is R naught over 3. If it's less than or equal to 1/10, use lump heat capacity. Greater than 1/10, use approximate solutions. If you use lumped heat capacity, what can you find? You can find the temperature at any time of the body. It doesn't matter, the center temperature is assumed to be the same as the surface temperature. The temperature everywhere in the body is the same at any one given time. So temperature is only a function of time. You can also find the amount of energy transfer that's occurred over that time interval. Q in joules. Q is in joules, not watts. Big Q's in joules, little q's in watts. Okay, two equations then you should have there. If it's approximate solutions, you can find one of three things. Really just two things, but we'll say three things. You can find the temperature at the center. The center of what? The center of the wall, the center line of the long cylinder, or the center of the sphere. There's another equation which gives you the temperature at any value, for instance, of x in time, or r in time, depends on what the geometry is. You can find the temperature anywhere, at any place in the body, at any time. That's the second equation. The third equation, you can find the amount of energy transfer in joules that's taken place between time equals 0 and time equal t. So three equations there now. But there's three equations for each of these three things. There's one for plain wall. There's one for long cylinder. And there's also sphere. So there's a set of 9 equations for these approximate solutions when the BO is greater than 1/10. 3 equations for plain wall, 3 equations for long cylinder, 3 equations for sphere. 2 equations for lumped heat capacity. Those are the important equations. That's it. But the equation for BO, okay. You go down here. When you have these solutions, you've got to find C1 and zeta 1 for the approximate solution. Values in table 5.1. To use this table, BO HL over K, or BO equal HR naught over K. We talked about that. The definition of BO changes between checking the BO number. First step, you go to table 5.1 for a long cylinder and a sphere. That's the BO number, which is different than the BO number over here for a long cylinder and sphere. So just be careful of that. Put those zetas and C1s in those equations and solve for the temperature anywhere at any time and the amount of heat transfer that's occurred. So it's fairly straightforward that way. It's organized that way. One other thing, use the approximate solutions. Somewhere you better check the Fourier number. And it better be greater than or equal to 0.2, or you cannot use the approximate solutions. In this class, it will always be greater than 0.2 if it's going to be approximate solutions. We'll never use the exact solutions, the infinite series, no. But still, I want you to check the Fourier number just to prove to me that it does satisfy that criteria. Check the Fourier number. Either before you pick the equation out, or if you're solving for time, solve for time, put it back in here, and make sure it's greater than 0.2. Okay, anything on that one now? Yeah, huh?
Your zero, it's like 0.106.
0.1, your choice, either way. Chance that happening, 1 in 5 zillion. What's a zillion? I don't know, it's a big number. No, I'll make that problem up, believe me, where you won't have to answer that question. I make sure when I do it, that it's pretty clear, it's less than 0.1 or greater. I don't want anybody round off on their TI, round it off, or picking properties off and not interpolating correctly and end up doing it the wrong way. That'd be my mistake. So what I do then is I make sure that it's either one or the other. Yeah, there'll be no doubt. And if you get close to 1, you'll probably make a mistake somewhere then. So check your numbers again. No, I wouldn't do that on you. Okay, now, that takes us into radiation, which is chapters 12 and 13. All right, before I do, now, yeah, I'll do that first, okay. Let's do 12 first, okay. We just had that several class meetings ago. I'm not going to go through a review on that per se, but what I'm going to tell you first of all is what things in chapter 12 you should be aware of and what things you can ignore. First thing, anything in the text or example problem that talks about something called the intensity of radiation, capital I, and our author does that in chapter 12. You'll see the word intensity. We didn't discuss that. We don't need that at this point in time. So anything with intensity, ignore. Ignore anything that talks about intensity in chapter 12. Number 2, if you see the word directional, now, let me tell you what this is, okay? This guy is called the total emissivity. This guy is called the spectral emissivity. Spectrum means as a function of wavelength. That's the lambda. This guy is called the directional. That guy is called spectral directional emissivity. Oh yeah, chapter 12 is big on definitions. Big on definitions. The language of radiation. What this means is that the emissivity might depend on the direction that it's emitting radiation. Is it emitting radiation normal to the surface, vertically up, at 45 degrees from vertical, at 70 degrees from the vertical? If epsilon depends on the angle theta, measured from the vertical, that's called directional emissivity. If you see the word directional anywhere in the textbook or problems in the textbook, don't look at it, don't work it. You're not responsible for anything with a subscript theta on it. Okay, lambda, yep, you're responsible. But these guys, no, we won't get that detailed in our discussion of radiation. Okay, so now we go to chapter 12. I'm going to go through chapter 12 and tell you which example problems are good to read and which ones you can ignore. As I told you before, because typically I pick my exam problems from the homework I assign, because I think it's important, the problems I work in class, because I think they tell a good story, and the textbook problems as examples. Those are the 3 sources I use typically for exam problems. I might tweak them, change what's asked for, change the numbers a little bit. Maybe work the problem for black surfaces for homework, and I'll make that surface have a particular emissivity 0.6. Okay, let's go through. Anytime you see the word directional, no. Intensity, no. Example 12:1, no, don't read it. It talks about intensity, no. Let's see where 12:2 is here. Oh, here it is. That's 12:1. Oh, 12:2, yes, it's a good one, read it. 12:3, no, it talks about intensity, no. 12:4, yes, read it. 12:5, I think that's emissivity, no, 12:5 was a no. 12:6 was a yes. 12:7, no, it talks about theta, theta's no. 12:8, yes. 12:9, yes. 12:10, yes. 12:11, yes, and a chapter. Up 12:12, no. Environmental radiation, no. 12:12, no. It's not a science section anyway, just so you know. Table 12:4. I think I got that on the, put that on the data package. Glossary of terms. It's a real, the author put it there because it's, as I told you, chapter 12 is pretty much the language of radiation, but it has all these words defined. So if you ever get confused, I'll just read a few. It's on 2 pages of words. What's black body, what's diffuse, what's emissive power, what's emissivity, what's the gray surface, what's irradiation, what's Kirchhoff's law, what's Planck's law, what's spectral mean, what's the Stefan-Boltzmann equation, what's total mean, what total means, over all wavelengths, over all angles. What's transmissivity, what's the displacement law, everything is there in that table, so if you get confused, you might want to put a few things down on your equation sheet. You're about to bring one equation sheet again, an equation sheet, both sides, same rules. So that's just helpful. The author did that to be helpful. Okay, and we went through a lot of problems on 12. 1262 on the homework set. That's the glass, plain glass versus tinted glass. If you have a question on that, we can go over that after class or office hour. But I did one in class similar to that. I did one in class like 1269. That one combines some convection heat transfer with radiation. But again, that was pretty straightforward. 72, I worked one in class like that, and that would be 3 problems out of chapter 12. Then we start chapter 13. I worked 2 problems out of 13.1. I gave you 2 more to work, 3 more to work. So those are pretty straightforward with the hints I gave you. I graded 13.2 parts B and C. Part A I described in class, so I didn't grade that one. But B and C I didn't talk about in class, so I graded those 2. Make sure when you get your view factors they're less than 1. Some people got greater than 1. You can't have more energy than 100% transfer. So you know if you're right or wrong if you get 6 on that answer. You misread the graph product. 0.6 is the answer, 6.0. 13.9, I set that problem up for you in class, 13.9. I won't go over that. Okay, let me do one right now, and then we'll come back to 13.19. But let me do the last problem because I didn't go over the theory in class, and I want to be sure you have the theory on that. Problem 1356 talks about radiation shields. So, radiation shields. Okay, the problem is we have 2 surfaces facing each other. This is area A1 facing area A2. And we'll assume that T1 greater than T2 will assume large surfaces. Okay, we have epsilon 1 and T1. Over here we have epsilon 2 and we have T2. A radiation shield is something put between a hot and a cold surface to cut down on the radiation heat transfer. So here is the radiation shield. Call it AS, area of the shield. So this is the radiation shield. Oh, typically the emissivity of the shield, I picked a number on the back of the book, 0.05, very low emissivity. Typically what it is something like a thin sheet of aluminum foil. That's essentially what it looks like. A very thin sheet, like it's aluminized mylar, but like a piece of aluminum foil in your kitchen. You put that between a hot surface and a cold surface, and what it does is it cuts down on the total radiation heat transfer from the hot surface to the cold surface. To see what's going on, you do it this way, let's say with no shield. So with no shield, here's what we have. This one right here, we have F12, and this one right here, there we go. This is EB1, this is EB2 for our little circuit. 1 minus epsilon 1 over epsilon 1 A1, 1 minus epsilon 2 over epsilon 2 A2, 1 over A1 F12. Now, here's what we have with one shield. Okay, let's start. We need a lot of space here. Let's start over here. I'll do it here. EB1, surface resistance, space resistance, surface resistance. Other side of the shield, surface resistance, space resistance, surface resistance. EB2. Surface resistance, 1 minus epsilon 1 over epsilon 1 A1. 1 over A1 F1 shield. 1 minus epsilon shield over epsilon shield A shield. 1 minus epsilon shield over epsilon shield A shield. 1 over A shield F shield 2. 1 minus epsilon 2 over epsilon 2 A2. This is the heat flow Q with one shield. This is the heat flow Q with no shields, 0. This middle node is EB shield, EB shield. So, we can play some numbers game. Say that the emissivity here is, let's say epsilon 1 equal epsilon 2 equal 0.5. Okay. So, notice the areas are all the same. Why? It says assume large surfaces here, 1, 2, 3. The area 1 equal area 2 equal area S. So you can make this Q double prime if you want and get rid of the areas. It's easy on the board with my finger, but I know, it just, you know. You can get the areas out of there. Okay. Make it double prime. Now play the game. 1 minus a half divided by a half. 1 minus a half divided by a half. 1. F12. Oh, that's simple. Without the shield here? Everything leaving surface 1 eventually hits surface 2. You got it. F12 is 1. Equivalent resistance. 1 plus 1 plus 1. 3. Okay, not him. First of all, why are there two guys epsilon shield on both sides? Because, I'll draw the picture here. Surface resistance, space resistance, surface resistance, surface resistance, space resistance, surface resistance. There are those 6 resistors over there. There is a surface resistance on the left-hand side of the shield and a surface resistance on the right-hand side of the shield, and they're equal. I'll make this Q1 double prime. Get rid of the areas are all the same, get rid of them. Divide through both sides of the equation for the Q, the heat flow by the area. There they are. 1 plus 1 plus 1 plus 1. 1 minus 0.5, 0.95, divided by my 0.05, that's 120, 0.05, 120. 10 times 9.5, 0.95, 9.5, times 2, 18 ones 19. You wonder why the radiation shield works? I'll tell you why. When you put the shield in there, you get a very, very large resistance. And what's the total resistance now of just adding one thin sheet of aluminized mylar? Okay, 38, 39, 40, 41, 42. 42 compared to what? Oh my gosh, look at that. Truly amazing, truly amazing. So what do you think they put in the shuttle bay when they launched the shuttle in the past? Open the bay doors, look in there, hanging from the walls of the shuttle bay were these shields in a blanket type setup. Yeah, because what are you worried about? Oh, solar radiation on the inside of the bay, shuttle bay. How do you prevent the heat gain from the sun? You put shields between the sun's radiation and the skin of the indoor bay. Yep, these two guys right here, because they're aluminized mylar, yeah, that really makes it a big resistance. Just with one shield. One shield. Now, what if you had N shields? Q or N shields. You can prove this. It's 1 over N plus 1 Q with no shields. What do they typically put in the shuttle bay, for instance, or in space applications on space? And by the way, in space, there's no air, there's no convection here. So you don't have any convection. The sheets don't touch each other, so you have no conduction. So you have no conduction, no convection. All you've got is radiation. And because you chose aluminized surfaces, radiation is cut down dramatically. Typically on space applications, they put 27, 28, 29 shields. 27, 28, or 29 shields. Not one shield. 27, 28, or 29 shields. What does that mean? Q with 29 shields is 1/30 of not having any shields. You cut down the heat transfer by a factor of 30. 30. You had 30 watts, now you got 1 watt. That's why they used these radiation shields in space. They're used on the surface of the Earth too. They're used in certain applications, terrestrial applications too, but their value really is high in space applications. Because what are you worried about at launch time? You're worried about weight. And what does a thin sheet of aluminum foil weigh? I'll tell you, almost nothing. Almost nothing. You pay no penalty, weight penalty for launch. because you've got these very thin aluminized sheets for protection. Okay, so this is what you, this one here. And then I'll just put this down. Q1 to 2 equals sigma T1 to the 4th minus T2 to the 4th divided by, I'm going to call them this, R1 plus R1 shield plus R shield plus R shield, R shield 2 plus R2. That's what you have for one shield. And of course, the one for no shields, get rid of these three resistors here. Knock this guy out, this guy out, this guy out. Now you've got three resistors left with no shields.
Question.
Mm-hmm.
For QN, why does the emissivity of the shield not play a role in that?
Which one again then?
For QN, or the equation for QN?
Oh, yeah. Why does it what again now?
What is the emissivity of the material you're using as the shield?
Oh, yeah. When you're doing this, these two guys can change depending on that. If you assume black surfaces, it won't matter. Won't matter. So you have to tweak that for that, yeah. Now, don't forget too, with no shields, do you have these two guys in here? Yes. One shield, these two guys still in here? Yes. 30 shields, these two guys still in here? Yes. They're always in there, yeah, always in there. All right, so that'll allow you to do the homework problem 1356. All right, so now let's start with that 1319 problem. I'll put that here, 1319. Okay. Here's the picture that we've got for 1319. It's a circular cylinder with a small area here. Let me make sure I get these guys right. A2 is the top surface, A3 the side surfaces. A2, side walls, A3. Problem says they're all black surfaces. Determine the value of F13. Calculate the net radiation heat transfer from A1 to A3. Okay. All right, let's look at F13 first. 1 is a small surface and 3 is a bigger one. Diameter is 3 meters on A2. The spacing between the two is 2 meters. Yeah. We're supposed to find F13. All right. First of all, there's no table. There's no graph figure in the textbook that allows you to find F13 directly. You can't do it. You have to do it indirectly. So you know what, I can't find that, but I think I can find F12. Okay, so F12, I go to figure 13.6. And this is F12, and this value figure 13.5, I think it's the wrong figure. 13.5. And let's look at figure 13.5. 13.5. L over R1, this is L over R1. And the parametric curves are R2 over L. This is R2 over L. Okay, so I go on the graph. This is 2 and 3. So R2 equal 1.5, L equal 2.0. So R2 over L is equal to 1.5 over 2.75. So I go to the line labeled 0.75 on the graph. Got it? Then I need, for the x-axis, I need L over R1. But he gave me a big hint. He said, you know what? That's a small area. Okay, good. So I know R1 is small. That means something divided by a small number must be large. Okay. L over R1 is large. Where's large on the graph? Far, far to the right. Far, far to the right. How far? I don't know, but it's big. What happens to the curve when you pass a certain point? Oh, look what happens to the curve. It flattens out. So for big enough L over R1s, it's not changing. Go back here. I got it. Now I've got F12. I'm not supposed to find F12. Find F13. Okay. Enclosure law. F11 plus F12 plus F13 equal 1. Surface 1, plane surface. F11, 0. F13, got it. 1 minus F12. Check. Okay. Q13. Q13 equal EB1, big number, EB2 divided by 1 over A1, F12. This should be a 3, excuse me. 3, F13. Let's just make it simple. A1, F13. Okay, there it is. If you want to draw the circuit, here it is. This is 2. This is Q1. This is Q2. This is Q3. Q1, 2, 1, 3, pardon. Q1, 2. Q2, 3. I'm not going to put all resistances in there, but there's one of the space resistances. So, if sometimes you don't see things like this equation I wrote down here, maybe it's helpful to draw a graph of what's going on. The equivalent thermal resistance network for radiation. What am I supposed to find? Q13. In this picture, where is it? Right here. What 2 things do I know? EB1, EB3, and that resistance. So, Q13 is EB1, the big number, minus EB3, the smaller number, divided by the resistance, 1 over A1, F13. Same thing as that. But let's just say somebody asked you to find Q1. Okay, Q1. Q1 is Q13 plus Q12. Can I find that one in this one? Of course I can. Or they might ask you to find Q3 or Q23. How many Qs are there? Well, count them up. There's 6. Somebody can ask you to find any one of those 6 Qs. This problem, 1319, just ask you to find one, but be ready to find any of them. Be ready to find any Qs. Okay. Sometimes a sketch helps. You can visualize things more readily. Try and find Q1 from that without that sketch. You can do it, but you want to take stress off yourself on an exam. You draw a picture. Pictures sometimes cause things to light up in your head, like, oh yeah, now I see what he wants to find. Okay. I don't know, where's area 4? I call that area 4. You want to find that's area 4. Does it play a role anymore? Not right now. Not right now. Okay. Okay. Now the radiation leaving here gets to 4. Okay. So what's the resistance? R4 to 1. 1 to 4, pardon me. What's F1 to 4? F1 to 4, 0. What's that resistance? Infinity. How much heat flows? None. If the resistance is infinite, there is no heat flow. So there's no such thing as a Q4 in that thing. From Q4 to 1 directly. Okay. 4 to, oh, not 1 to 4 directly. Okay, so let's try a next problem in line. Anything on that before I go on to the next one? Yeah.
On that figure, I just want to make sure this label's right.
Yeah.
1 and then 3 to the right.
Yeah, yeah. Oh, yeah, thanks. Make that this way, thank you. I'm used to putting 2 on the right and 3 down below. Thanks. All right, let's take a look at another one now. Our next one in line. I'm going to put that over here. That might need some more space. Okay, 1319, 1321. Not 13, 20, okay, 1321. I'm going to put that right here. All right, so we have a circular disc up here with a heater. This is a heater disc. There is a circular surface down here that's kept at 500 K. The heater, we don't know the temperature T1. This is surface A1. Let's go this way. This is surface A1, this is surface A2. And then this in the large room whose walls are at 300. Okay, that's what we're given. And they're all valid. Okay. We know the dimensions, diameters, and the spacing of the disc. Find T1. Okay. We know the heater provides heat. Some of that heat goes down to A2, and some of the heat goes out the sides to the room walls. If it helps, look at the picture again. All black surfaces. Which one's the heater? Here. What's Q1? The power that comes into the heater. what did he say? The power that comes into the heater is 17.5 watts. So right now, I know Q1 equals 17.5 watts. He told me the power that comes into the heater. Electric power. Okay. I set up here in a picture. Where does that heat then go that leaves A1? Some goes to A2, the bottom, and some gets out the sides to the surfaces around it. A3. You can call the surroundings that. So it's equal to Q1, 2 plus Q1, 3, where 3 surroundings. And if you want to, don't forget these are enclosures. If you want to make an enclosure out of it, you put a fictitious surface. Here's the dashed line. And you say, you know what? I'm going to call that A3. It's circular. It's part of a cone, circular. How does that A3 behave? Here's what it comes in. A3 behaves as if it were a black body at the temperature of the walls in the room. A3 behaves as if it were a black body at the wall temperature, 300. So epsilon 3, you assume is 1. The temperature of A3 is 300 K. Okay, there it is right there. Do I know, let's get A1, F12. Well, here's Q12, all right. So Q12, sigma T1 to the 4th minus T2 to the 4th divided by, let's just put it in front of it, A1, F12 plus A1, F13, sigma. There it is. Do I know F12? Sure I do. I go to figure 13.5. I go to L over R1. I read up. I go across. I read F12. Got it. Figure 13.5. Can I find F13? Of course I can. F11 plus F12 plus F13 equal 1. F13, 1 minus F12. All right, in the equation, what do I know? I know A1, F12, sigma, A1, F13, sigma. I know T1, I know T2, I know T1, I know T surroundings. Oh, I don't know T1 part yet. Solve for T1. All right, that's it. That's how you do it, yes.
For 1319 and 1321, I believe that there were equations in the table that let you solve for F1, 2.
Yeah, that's right.
Okay.
Yeah, your choices on the exam, for instance, your choice would be, you use figure 13.5 are the equation.
Okay.
That's fine, that's fine. Okay, let's do, yeah, I think this is the last one, 1323. Okay, this is a tubular heater. Okay, so it looks like this. I have to, yeah, that's okay. So the heater is supplying heat, it's circular. And there's a disc out here. We know all the dimensions. The disc diameter, the heater diameter, the spacing L, we know all that. The surfaces are black, surface, the heater, assume black surface. The temperature of the surface is 1,000. Temperature is equal to 1,000 K. We're going to call this surface A1. We'll call the heater surface A2. And we want to know, he says, find the radiant power from the heater which is incident on the disk, QS to 1. I don't want to say S, I want to say the heater is area 2, so 2 to 1. 2 to 1. Now, let's take a look at it. Is that an enclosure? No. Could I draw something like that? Probably not. It's not an enclosure. Is it in a big room? It didn't say so. Are the room walls given? No, they weren't. No, no. No, it's not an enclosure. It's not the large room, like the last one we worked. No. This may be a misnomer. I'm not going to write that down because that's really not what that is. Okay. Find the radiant power leaving A2 that gets to A1. That's not Q12. Q12 is the net radiant exchange between two surfaces. This is not the radiant exchange. This is not the net. All they want to know is this surface A2 is radiating energy, and some of that gets out this side of the hole and strikes A1, and some gets out here and strikes A1. That's what they want. Here's a circular heater like that. You heat the inside surface. Some radiation gets out that hole and strikes that small little quadrant. This is a tube. That's a little surface, a diameter quadrant there. I don't want the net exchange. I don't want Q12. I want this in words. Is there a shorthand notation for it? Well, let's go back to the start, the very start of chapter 13. Okay, the very start of chapter 13, this is the first thing I put on the board. I said, here's surface A1, here's surface A2, and of all the radiation leaving surface A1, only a part of that strikes A2. Here's what I wrote down. I said, that radiation is equal to what leaves surface A1? J1A1. What's J1 radiosity? What's its units of J1? Watts per square meter. Multiply it by an area, square meter. What's J1A1? Watts. The total watts leaving surface A1. A fraction of that gets to A2. A fraction. We said that fraction is F12. So that was A1, F12, J1. What's J1? Epsilon 1. Sigma EB1 plus the reflected energy times what comes in. Surface 1